Okay, so Unit 3, Lesson 2 and 3, we're going to kind of do them together. They're a little bit different, but 2 is based off of 1. We're talking about greatest common factor, so GCF. GCF is something you're going to see a lot with factoring and you want to be good at. So, for example, the GCFs of 8, 16, and 20 is the biggest number that goes into all of them, okay, which would be what? It's the biggest number that goes into 8, 16, and 20. 4, good. So 4 would be our biggest number there, okay? And then we move down here. We'll say the greatest common factor of these guys. 5, good. 18 and 20. 2, yep, it's only 2. And then 36 and 54. Nope. Nope. Bigger. No. 18. 18 times 3 is 54. 18 times 2 is 36. Okay, good. All right, so in the example above, parts A and B were fairly simple to do, but part C was more complicated because the number was a large factor. So a lot of these ones are kind of easy to see because they're lower, because you guys start low. I mean, just naturally, we know 2 goes into it. We know that 5 goes into it, so I feel good about that. So in a case like this, we can use prime factorization to help us. Now, the reason you really do this section is to be honest with you, these trees and stuff that we've been doing, those are going to go away. Okay, what I mean by that is you're not going to use them all the time. This is to help you get a number sense. We're improving your number sense. So when you guys get into factoring, you get into things where you're like, next time probably in grade, Math 20, if I ask Brandon about this, he's probably be like 18. Because he remembers, he's like, oh, 18 goes into 36. I got that down. Okay, so if you're getting like upset or don't really like these tree things, they're not going to be around forever. They're just to help us with number sense. Okay? Okay, so let's get to the next one here. All right, I'm going to go and do what they're talking about here. So it says use prime factorization to determine the greatest common factor of the given whole number. So we're just going to break 90 and 225 down as far as we can to their prime factorization. So using the trees. Okay, so we'll start with you, Ali. What goes into 90? Just give me a multiple of 90. 10 times 9. Okay, and then Ali, what can we break 10 down to? What can we break this down to 10? 5 times 2, right? Okay, good. And then I'll help you finish it, Ali. What's the 9 break down to? 3 and 3, right? Good. Okay, so that's my factorization of 90. Okay. 225. Tatum, just give me something that goes into 225. 5. Okay, I think it's, what is that? 5 times 45. Okay, so 5's done. Tatum, what goes into 45 now? Nope, no, not quite. 5, yep, 5 again. And then a 9, and then we can break the 9 down to 3 and 3. Okay, so here's what we do this is how you can find GCF. This is when you don't know, like bigger numbers like this. Okay, you take the prime factorizations they have in common and you circle them. Okay, so 5 and a 5. 3, 3, 3, 3. Okay, so these 3 compared to these 3. So then what you do is, what's 5 times 3? 15 times 3. 45. This one's GCF is 45. It's those 3 prime factorizations they have in common multiplied. Make a little bit of sense, maybe? Okay. Xander, what's the number that goes into 154? Any number. 2. Okay, and that's 2 times 77. Okay, what goes into 77, Xander? 11? Is that what you said? Yeah, 11 and 7. 7, 11, 2. Those are all prime numbers, right? So that one's done. Okay, 198. Brandon, what goes into 198? 2, and what's that, 99? Okay, and then what goes into 99? 11 and 9, and then the 9 breaks down to 3 and 3. So we go back to our highlighter here. They have a 2 in common. They have an 11 in common, and that's it, 2 and 11. So what's my greatest common factor? 2 times 11, 22. Okay. Okay, so we got a couple more here. Wait, did I skip it? Oh yeah, these guys. Okay, so use prime factorization to determine the greatest common factor of the given whole numbers. Okay, so we're doing the same thing. They use this one as the dividing bars, but I think we kind of like the trees better, so we can keep using those. And so 245, what goes in 245, Janae? 5, that's what, 40 or 49, okay, and then what's 49 break down to? 7, 7, that one's done. Okay, good. 315, what do you think, Molly? 5, good. What is it? Keep that for me. 63. 5 times 63, and then what's 63 break down to? 7 times 9, and then 9 breaks down to? Okay, good. And then 770, Breezy. Yeah, 10 works. 10 times 77, and what's 10 break down to? 5 and 2. Yeah. And then 77? No. Think about, we did 77 already. There you go. Okay, 11, 7, 5, and 2. Okay, so now let's go through and find our similar ones. They all have a 7. Whoops. That's not what I wanted. We'll go black 7. Whoops, that's red, but it's okay. Highlighter. Okay, they have a 7 in common, a 7 in common, and a 7 in common. They have 5s in common, 5 and a 5. Is there anything else? No. So 5 times 7 is 35. So 35 is this one's answer for their greatest common factor. Okay, let's keep going around the room. Let's participate in here. So what can you break 171 down to, Allie? Three. Okay, we'll give her the 3. It's 3 times 57. Okay, what can 57, who goes into that? I think 3 again, huh? 3 times 19. Okay, 19 prime. So we're done. 3, 3, and 19. Okay, all right. Let's do 399, and then I'll do another row here. We'll do 285 down here, so we have some more room. So 399. We'll get to that. What we got in that one? Xander or Tatum? Sorry. 3. What is that one? 3 times 33. Bunch of. Oh, 133. Okay, and then does 133 go down at all? What's the 133 go down to? 719. Oh, okay, got another 19, huh? Okay. All right, then we'll try 285. Xander, what's 285 trimmed down to? 5, okay, and then 57. We already did 57, didn't we? So we got 319. Okay, and then 1140. Brandon? 2, sure. What's that? 570. Okay. You did by 5 again. Okay, and you got what? Say that one again. 114. Okay. Okay, and then that's 57. And then 3 and 19. So let's kind of see this problem here. Look at the number that kept coming up. 57, 57 kept coming up. Okay, so let's go see if we can figure out what do they have in common. They all have a 19, right? And a 3. Is that it? So then 57 is the common number, huh? 57. Good. All right, let's continue here. All right, lowest common multiples. So that means like where they meet when they multiply, like where they overlap. So, for example, 5 and 12, they meet at 60. Okay? But anyways, so LCM, that's the least common multiple is what it's talking about. Okay? So like multiples of 6, 6, 12, 18, 24, 30, 36, etc. 8, 16, 24. So the least common multiple of 6 and 8 is 24. Okay? That's their least common multiple. That's, common means the same. Okay? So you put 24 right here on your notes. I'm going to move mine up. Okay, now least common multiple, well, is it always going to be just 5 times 7? No, there's sometimes ones that are before that. Okay, so this one is going to be 35, but that's not always the case. Okay, 35 is where 5 and 7 meet up. So 10, 15, and 20. So we're trying to figure out, okay, 10, 15, and 20. What's that going to be? 60, good. 60. 10, 12, 14. Let's see if you can find this one the fastest. It's one of those bigger ones again. They're making their point. I almost don't want to stop you because you've been working so hard. All right. So this one's going to be in 420. 420 is the least common multiple of those three numbers. So the example above, parts A and B were fairly easy. Part C was a lot more difficult, took a lot more time. So to determine the least common multiple, take all prime factors of one of the numbers and multiply by additional factors in the other numbers. So take 2. So we breaking 10 down. 2 and 5, 2, 2 and 3, and 2 and 7. So we take 2 and 5 from 10, 2 and 3 from 12, and 7 for 14. So these are all the ones that are kind of different. So they have all these in common, right? So then they're multiplying by 2, 5, 2, 3, 7. 2, whoops. Hold on here. Oh, I see. So if they have them all in common, that only counts once. Okay, that only counts once. That's how they're doing it. Okay, so if they have 2, 5 from 10, 2, 3 from 12, and 7 from 14. Okay, so you're taking the 2, 5, the 2, 3, and the 7. Okay, then you multiply all those, and that will get you 140 or 420s. 420, sorry. Dyslexic again today. Hi. Okay, 420. All right, so let me explain one more time about this 2 thing. Okay, you take the prime factors. So I take this and then any additional ones. So this one, the additional is the extra 2 and the 3, and this additional is 7. So like I said, this 2 right here only counts once, but there's 2 2s, so we have to have 2 of them. Okay, so again, 1, 2, That doesn't count because it's canceled by that. That's the second one. 3, 4. Doesn't count because we already have 1, 2, 5. That's our 5 numbers to find the LCM. All right, let's do some examples here. Okay, so for example, 15 and 35, this breaks down to 5 and 3 and 7 and 5. Okay, well, see how they share a 5? So I only use 5 once. I just go 5 times 3 times 7. So their least LCM is 105. Does that make a little sense, hopefully? Okay, I'll try another one here. 126, I'll go 63 and 2, and then 7 and 9, and 3 and 3. 441, 3 and 147. 3 and 49, 7 and 7. Okay, so let's go for the first one. I have a 2, a 7, a 9, and a 3 and a 3. 2, 7, 9, 3 and 3. Okay, on this one, I have 2 7s, so it gets me an extra 7. I had a 7 already. I had a 3 already. And I had another 3 already. So I have 2 3s here by those 2 3s. I have 2 7s, so there's only 1 7 over here, though. So that's where we get the extra one. So your LCM here is all the yellow multiplied. 2 times 7 times 9 times 3 times 3 times 7. It's a big one. 2 times 3 times 3. Oh, not 9. What am I doing? Sorry, we have 3 times 3 is a 9. Disregard that. Okay, so it's 2 times 7 times 3 times 3 times 7, which gives us 882. Okay. All right, let's try this last one here. There's 3 of them. So we get 11 times 2 here for that piece. That's done. Okay, 154, we're going to go 2 times 77. And then 11 times 7. And then 198, we're going to go 2 times 99. 11 times 9. And 3 times 3. Okay, so again, I have an 11, so that cancels all the other 11s. I have a 2, that cancels a 2. So that's kind of done. That's done. That's done, and that's done. We've covered that 1, 2, 1, 11 from each. Okay, the new one from this one is 7. Does not have a 7, and then 2 3s. Okay. So this one we're going to be at 2 times 11 times 7 times 3 times 3. 5. Yep. So this one's LCM is 1386. 1386. All right. Almost there. I think maybe we'll just do this one today. I feel like this is long. Okay, so prime factorization of a perfect square. So when you prime factorize a perfect square, what do you think is going to happen? When you're prime factoring a perfect square, what are you going to have at the bottom? Yeah, you're going to have pairs of the same number. So for example, this obviously is going to be 3 times 3. Well, this is 9 times 4, which gives you a 2 and a 2, a 3 and a 3. See how you have 2 pairs? Okay, that's how you're going to do prime factorization for perfect squares. And then this one here would be 7 and 7, 8 and 8, which goes to 4 and 2, which goes to 2 and 2. So 2 2s, 2 2s, and then 2 2s. So there's 3 pairs in that one. Okay, 2 times 2, 3 times 3 for 36. Okay, and then that's why they're showing you the square root of 36 is just whatever your pairs are. My pairs are 2s and 3s, so 2 times 3 is my square root. Square root of 36 is 6. Okay, 49 is 7 times 7. Square root of 49 is 7. 64, we got it down to they broke it down 2 times 2. I bet you. What are they putting there? Oh, gotcha. Okay, 8. Okay. All right. Okay, so consider the number 44,100. Okay, so use a calculator to find the square root. So what's the square root on your calculator of 44,100? 210. So you're going to get 210 from your calculator. So explain how you can use the prime factorization to verify your calculator's answer. Well, we could break it down. Okay, so we can break it down, and we should have all pairs at the end, right? This is a perfect square. We should have all pairs at the end. So the first one they went 100 times 441. Then they went 10 times 10, 5 times 2, 5 times 2. 441, that breaks down to 9 times 49, which is 3 times 3, 7 times 7. We have a pair, 5s, and we have the 2s. So we have 4 pairs there. And if you multiply 5 times 2 times 3 times 7, you're going to get 210. That's the number of cents we're looking for. Okay. Next two, with the auto calculator, they want us to determine if they're perfect squares or not. So we're just going to do prime factorization and see if we have pairs at the bottom. Okay. So 1225. What do you want to start with? 5 or see what I start with here? Yeah, I start with 5. Let's go 5 times 245. I'm going to break that down. 5 times 49. 7 times 7. I have a pair. So this is a perfect square, and the perfect square is what? It's a pair of 5s and a pair of 7s, so your perfect square is 5 times 7, so 35. So your perfect square of this number is 35. Okay. 3,042. 2 times 1521. 3 times 507. 3 times 169. And I have 13 times 13. So is that a perfect square? Yes? No? No. We have a pair. The 2's left off. He doesn't have a pair. Not a perfect square. Okay? Good deal. Okay. So then with perfect cubes, what do you think we have to have groups of? Yeah, 3s. Where did I go? Oh. Okay, there we are. Okay, so perfect cubes, yeah, we're looking for groups of 3. So 27 breaks into 9, which breaks into 3 times 3. 27, that's 3 3s right there. Okay, that makes 27 perfect cube. 27 is 3 cubed. 216 breaks into 6 and 36. 6 and 6, again, we have 3 of them. So 216 is 6 cubed. You put 6 cubed in your calculator, so kick out 216. And 3375 breaks into 5 times 675. And breaks into 5 times 135. And that breaks into 5 times 27, which we know 27 breaks into 3 and 3. So we have 3 5s and 3 3s. So what's our perfect cube? What's 5 times 3? 15. So it's 15 cubed on your calculator should be 3375. Okay, all right, finish this up here. Last example. Okay, in each case use prime factorization to determine whether the number is a perfect cube. If the number is a perfect cube, state the cube, root, and the number. Okay, so 6912. So let's just break it down. What goes into that? 2, 3, 4, 5, 6. Okay, we can go 2 again. 1, 7, 2, 8. So we can go 2 again. I have 8, 6, 4. A lot of 2s. Maybe I should have done 4. Okay, 432. Everything's even. Okay. So let's come up here. Let's do 108 over here. 2 and 54. And then we finally run to the end. 2 and 27. And we know 27 is going to work out to be our group of 3s. All right, so let's take a second here. So I have 1, 2, 3, 4, 5, 6, 7, 8. Am I missing one? No. Okay. And then I have my 3s. 1, 2, 3. So I have 2 to the 8th, and I have 3 cubed. So that's cubed. Is 8 divisible by 3? It's not. So this is not a perfect cube. It's off by 1. We need one more 2, and we've been good. Okay, so we're close. Let's try this one. 3. It's a big number. 3, 2, 3, 4, 3, 3. Got 3 again. 107, 811. We do have a 3 again. 3, 5, 9, 3, 7, and 3 again. 119, 79, and the last 3 here gives us 3993. Then they go to 11. Like that. Okay, so we have 1, 2, 3, 4, 5. I think I skipped one, didn't I? Yeah. Sorry. Skipped one spot. 3 times 1331. Sorry. And then it got to the end there. Where that was 3 times 3993 divided by 3. 11. Okay. These trees are keeping me mixed up. Sorry. 11, 121, and then 11. Run out of room down there. Okay, so basically there is 3 to the 6th, and then 11 cubed. So we have that's divisible by 3, that's divisible by 3, so it is a perfect cube. Long story short there. Okay, and that would be it.